Good morning, everyone. Welcome to VMworld. Welcome to Barcelona. Sorry for the delayed start. I guess the plenary has some exciting features today. So today we're going to talk about Storage DRS. But before I begin, I'm going to ask 3 questions, okay? Just to get a show of hand in the audience. So can you, who in the audience have deployed ESX 5.5 in their environment? Wow, that's a pretty aggressive deployment. Second question, how about who in the audience is using currently in their environment storage I/O control? Okay, again, and the last question, how about the same for storage DRS? All right, then. So I've got some interesting features and exciting things to report in this talk, and let's get started. Before I begin, there's some disclaimers we have to do. So there are going to be some things that I'm going to be talking about. They haven't been generally released yet, so bear with me. And then, some of the things may be released, this year or next year. So we'll come to that as we go along. So what we're going to do today, we're going to start with the bottom up. We're going to start with the ESX scheduler. And since many of you have already deployed ESX 5.5, I thought I would start with the new I/O scheduler in the ESX 5.5. Then we're going to talk about the new control in the new I/O scheduler, which is the I/O reservations. Next, we're going to look at the storage I/O control, how that the ESX scheduler comes together to provide performance features in terms of capabilities of controlling the congestion in the environment. Next, we're going to talk about the new I/O control in storage I/O control, which is the I/O reservations. Then we're going to switch gears and then talk about storage DRS. Instead of looking at a single data stores, we're going to look at how storage DRS manages multiple data stores in the environment. We're going to start with a couple of aspects of storage DRS. We're going to start with how storage DRS operates with the variety of storage features in the environment, such as thin provisioning, deduplication, and auto-tiering. Next, we're going to look at how storage DRS operates with the VMware features. The first one we're going to look at is the SRM, Site Recovery Manager. So what we're going to talk about is, how on the primary side the features of Site Recovery Manager interrupts with the storage DRS. Next, we're going to look at the other replication feature, which is the vSphere replication, and look at how on the secondary side of vSphere replication manager, if you use storage DRS, how would that work out? Okay? So that's the general outline of the talk that I'm going to go through today. Now, good news. So many of the things that I will describe in this talk is already available in vSphere 6.0 beta. Has any of you have tried the beta yet? Good. If you haven't, now is your chance. Go ahead and then try to sign up. And if you find anything odd, anything not desirable in your environment, please let us know, because this is the time for you to give us feedback of how the vSphere 6.0 would look like. Okay. So let's start with the bulk of the talk. Okay. So what's the problem? Okay, so let's start with the simple problem, and then we're going to build up the problem as we go along. Let's just say we have a shared data store, and then 2 VMs accessing that shared data store. Okay, one of them, these are sort of like an important VMs, and on a normal day, when they are accessing their normal I/Os, they're happy. Suddenly, there's a backup workload starts happening on the same data store. All the other VMs on that data stores, we started the backup. The problem here is that the backup workload is quite heavy. What that means is that the actual workloads that we would like to have performance, which is the order processing or our web servers, are now do not get the performance that they require from that data store. Okay? What we would like to see, if such a thing happens, is that, we would like the backup to go through, but in a pace that doesn't impact the workloads that are primary on that workload. So that's the primary problem that we're going to look at, how it is solved in the storage I/O control and storage DRS. Okay? So In vSphere, there are a couple of performance controls that you can use to solve this problem. The first one is called shares. Okay? Suppose we have a data store, and then that data store, just for an example, has about a 1200 IOPS capacity. Okay? If you set shares, which every VM has a default share to begin with, you can adjust the individual VM's proportional consumption of that workload. So for example, on the right, you see that the 1200 IOPS is being divided by 2 VMDKs, which has equal shares of 600 each. Okay? The problem with shares is that as you add more VMDKs, there's a kind of a dilution of performance. You know, on the left, for example, that you add a third VMDK. Now each one of them has equal shares, except the performance that the individual get is not 600 anymore. They are sharing the available performance in an equal proportion. Okay? So in this case, for example, like, you know, if you have shares, you know, everybody's getting roughly the same performance. Oh, am I doing in the wrong direction? Okay. So the second control is limits. Okay? You can also say that on a VM running on a data store, you can say, okay, that VM is going to consume no more than a certain amount of performance. So for example, you can set a limit on the backup workload that, like, you know, it can only consume up to 500 IOPS. No matter how hard it is going to try on that data store, it's never going to exceed that limit. Okay? But what that means is that if the other workloads are not using the data store, then that means, you know, that's the total performance that it's going to get, and no more than that. But we would like to have the last one that is coming new is reservations. So what we said is that, you know, what's the relative proportion? What's the maximum? Reservation is the minimum side of the performance. What you can say is that if you set a reservation control, a VMDK will be guaranteed to that amount of IOPS no matter what happens on the system. Okay? Okay, so this is easier said than done. Let's see how this is going to happen. So for example, in the case of the workload, if you set for the backup workloads, what we can do is that, like, you know, we start with equal shares, then you set some smaller share because it's not an important workload. You can set a limit on that workload such that it never consumes more than that. But also you can set a reservation in a way that, like, you know, no matter what happens, it will complete at a certain determined pace. Okay. So having the basic controls out of the way, let's look at the vSphere from the bottom up. So what we're going to do is we're going to start with the scheduler, with the ESX 5.5. Okay? We haven't done a good job of advertising it, but for those of you who have deployed ESX 5.5, there's a new scheduler running in that system. There's some differences of that scheduler, and then the primary difference of that scheduler is that it supports I/O reservations. So let's look at how the reservations are implemented and what does that mean in the environment. Okay? Let's just say with a simple environment, we've got a single data store, single ESX server, and 2 VMs running on it. The settings are such that VM A has 200 IOPS reservation, and then VM B has 100 IOPS reservation. They have roughly different shares. One of them is 1,000 shares, the other one is 3,000 shares. And then A has a limit of 500, whereas B has no limit. So okay, this is somewhat of a complicated example in the sense that both VMs have all the controls that are set. So let's look at what happens in terms of the performance that they get on that data store when things are congested, when things are everybody sort of like, you know, looking at the top I/O. Okay? So the table on the left shows the performance that each VM is going to get depending on the capacity of that I/O, of that data store. Let's start from the top row. If the capacity of that data store was 1,000 IOPS, this is again just for illustration purposes, what the scheduler will do is that it's going to start with the reservations. Well, do I have enough capacity to fulfill the A's and B's total reservations? Yes, I do. In fact, I have got quite a bit of more than the reservations. Once the reservations are satisfied, what it's going to do is that, if you see on the top row, it's going to proportionally divide the I/O based on the shares. Now, notice that the shares was 1:3 ratio. So that means every I/O that VM A gets, VM B will get 3 times more than that. So if the capacity were 1,000, you'll get about 250 on A and about 750 IOPS on VM B. Okay? But this is not always the case. Suppose the capacity wasn't 1,000, and suppose the capacity was 500. Now what happens then? Okay? Again, we start with the reservations. A gets its reservation of 200, and then B gets its reservation of 100. But now, the excess capacity beyond reservation is totally given to B because we really want to get 1-to-3 ratio of the shares. Note that we don't quite get it because there is not enough capacity to give 1-to-3 ratio. But the important thing is that A, both get their reservations, and then B, important VM, which is B with a high share, gets higher IOPS than A. Okay? The last row. So what happens if the capacity was 200? Not enough even to satisfy the reservations. Okay? The behavior of the scheduler, if such a case occurs, and it might happen in some cases, is that the IOPS that each individual VMDK will get is in proportion to their reservations. So in this particular case, A has twice more reservations than B, so that means it will get twice as much performance as VMB. Okay? So this was a simple example. We have a single data store, single host. So let's look at some of the other characteristics of the new scheduler. So I already told you about the reservation, which is a new feature in the new scheduler. The other thing that happens in terms of the new scheduler as opposed to the old one is that the accounting of IOs in the new scheduler has changed. In the old scheduler, each IO was counted as 1. Like, if it was 4K, 64K, 256K, it didn't matter. Each IO was always counted at 1. In the new scheduler, this behavior has changed, and that's probably one of the confusing things in the field today based on some of the blog posts that I see. What that means is that in the new scheduler, the IOs are accounted based on the size. So there's a normalization going on. So what that means is that, let's look at the old one. If you had using the ESX 4.1, for example, the old ESX, and you had a limit of 100 IOPS on a VM. Suppose, for the sake of discussion, that VM is doing 64 kilobyte IOs. Okay? If you were to upgrade to ESX 5.5, you'll see that the limit on that VM is still the same, the IO pattern is still the same, but it can only get 50 IOPS because the new scheduler breaks the IOs in terms of accounting purposes in blocks of 32 kilobytes. Okay? So each 64 kilobyte IO will count as two IOs in the new scheduler. So this is something you should be aware of. And if you have setting limits and reservations, these controls will always be quantized in that block size. Okay? So how do you know that you're running the new scheduler? Okay? It's really simple. If you look at any of the ESX 5.5 bugs and then look at the system settings, if the value that you see for the new scheduler with reservation, then you're running the new scheduler. You can also set back to 0 if the old behavior is the desired behavior and not the new behavior. Okay? Okay. So what we have done so far is that we talked about the IO scheduler in the single ESX box and how it introduces the new controls and the new behavior that it brings into the table. Now what we're going to look at, what is the performance of a data store across multiple ESX hosts. And we're going to look at the storage IO control first, and then introduce the storage IO control feature, which is the IO reservations that is implemented across the cluster of ESX hosts. Okay? So by now you know what shares mean. So what happens is that, so for example, if you had two ESX hosts that are locally, and let's just say they have each have their local data stores, each has a capacity of 600 IOPS. But for the sake of discussion, let's just say the host on the right, so host on the left has 2 VMs and host on the right has 1 VM. Note that everyone has the exact same share, except just by the virtue of running 2 VMs on the host on the left, the performance that they get is half the performance that on the other host. What we would like to do in a cluster environment is that, let's just say we have a bigger data store that has a total capacity of both data stores. And we'd like to make sure that when the shares are 100, they all get equal performance. But that's not quite what happens. Okay. The reason being is that as the IOs happen through the ESX on the left, notice that the amount of queuing that's going on is, there are 2 VMs on that host, whereas the 1 VM on the other host. So that means the VM on the right will get much higher performance than the VM on the left. So that's where storage area control comes into picture. So what it does is it coordinates the actual queue slot consumption on the ESX hosts such that the performance that each VM will get is based on the proportional of their shares. So in this example, what storage area control will do is that it shrinks the available queue slots on the ESX host on the left or on the right, such in a way that all 3 VMs will get equal performance of this data store to implement the shares. Okay? Notice that this is critical. You can't really implement this on a single isolated ESX host. The coordination across the ESX hosts are absolutely necessary to be able to control and provide these controls in a cluster. Okay? So how does it work? So storage area control does 2 things. Okay? First, you set a latency threshold on the data store. If the data store performance is in such a way that the latency threshold is never hit, everything is good. Everybody gets whatever they want, everybody's happy. If the latency threshold ever exceeds to that set amount, then the first thing that storage area control does is it detects this condition across a cluster of hosts in a distributed fashion. Okay? Once this condition is detected, storage area controls get into gear and then makes a divvying algorithm across the cluster of ESX hosts in such a way that each individual VM on that cluster running on that data store gets a performance commensurate with its resource controls, which is reservations, shares, and the limits. Okay? The primary mechanism that it employs to achieve its goal is really the adjusting of the queue slots on the individual ESX hosts. This is done in a coordinated fashion, such that the shared data store is always divided, the performance of the shared data store is always divided based on the controls of each individual VM on that data store. So how is this done? Or what this congestion threshold that I mentioned should be. Okay? So let's look at the graph on the right. So the top graph shows what happens to the throughput on a shared data store as the data store I/O load is increased. So what you will see is that as the data store load is increased, the more I/Os are happening on that data store. The throughput will go up, but there will be a point where the throughput will taper off. The graph on the bottom shows the exact same data store. What happens as I increase the data store load, what happens to the latency? What's going to happen is that the latency will keep shooting off once the throughput capacity of that data store is exceeded. So what typically should you do for storage area control is that you should set the latency threshold to the point where the data store IOPS capacity is about 90%. Don't worry, if you don't know what that capacity amount is, storage area control actually does compute it for you, and then will set automatically, if you do nothing, the latency threshold to the point where the throughput is about 90% capacity of that data store. Okay? This is by no means is a set, cast in stone. You can always go back and then change that setting to something that is lower value, which means that your overall latency on that data store will be lower, but you may not get the full throughput capacity of that data store. Again, this depends always on the kind of environment that and the kind of requirements on the workloads running on that data store. So I already mentioned that the new scheduler supports reservation. What about storage area control? Okay. So the storage area control is fully aware of the individual reservation settings of the VMs running on that shared data store. Up until ESX 5.5, reservation at the shared level weren't supported. In the upcoming release, if you can start experimenting this with the beta. When the I/O slots are being calculated across the ESX cluster, the reservation is now taken into account. That if you have VMs with high reservations, then even though the total shares on that host might be small, you'll get higher I/O slot capacity such that all the VMs on that host can achieve their reservations. Okay? So this is all and good, but you might ask, are you saying that at all times the reservations will be satisfied? Unfortunately, no. Because this implementation is a host-centric implementation. So what that means is that it will do, at its best, try to satisfy and make a division of the overall performance across the cluster to satisfy all the reservations. But there might be cases where reservations may not be satisfied. For example, there might be additional loads on that data store, or the loads might fluctuate, depending on some of the background loads. If those cases happen, the behavior reverts back to the kinds of behavior that I mentioned in the individual scheduler. So the reservations are always satisfied first, but if there is not enough capacity, the overall performance that each VM will get reverts back to the in proportion of their reservations. So the local behavior is continued to implement at the shared level at the cluster as well. Okay? But storage area control does one additional thing that the local ESX scheduler doesn't do, which is that if the reservations are not satisfied on that data store, and then this situation is sort of like some of a permanent situation, it will notify storage DRS to take further action. Now let's look at what that action might be. So what I have done so far is that I went through the storage area control. I described what the capabilities of that, and also looked at the reservations as the new feature that is coming in storage area control. Now let's look at storage DRS, and then let's start with how it reacts to the signal that I mentioned from storage I/O control where reservations weren't able to satisfy. Okay? Now, what storage DRS brings into table is recall that storage I/O control has always looked at a single data store. Whereas in the case of storage DRS, we have a data store cluster of multiple data stores. So at the I/O control level, the reservation enforcement is always monitored. And if it finds that the reservations are not met in one of the data stores, the signal comes up to storage DRS. And storage DRS will, in reaction to that signal, will try to rebalance the I/O load on those data stores in such a way that all of the reservations can be met. Okay. That's one important addition when storage I/O control and storage DRS work together. The second thing is that when you are making initial placement on that data store cluster, the reservations come into play. You can have reservations in one of two ways. You can have reservations as hard constraints, which is not the default, or soft constraints. If the reservations were soft constraint, that means the overall data stores will be allocated VMs to the amount where reservations on individual data stores can be supported. Okay? The other thing that storage DRS does is that it also computes on each individual data store what is the total reservable IOPS of that data store. Okay? And then this will show up as the sort of like higher capacity when the reservations are being balanced across the cluster. Okay? Now, so what we have done is we started from bottom up, we came up to the top. So what I'm going to do is that I'm going to shift gears a little bit and then go back to storage DRS in primary. But as I know many of you have already using storage DRS, but I just want to just reiterate some of the basic capabilities it does, such that we are all on the same page for the rest of the talk. Okay? So we already mentioned that there's a data store cluster concept where individual data stores are aggregated, and now instead of managing individual data stores, we are managing them as a cluster. Okay? So the first thing that storage DRS allows you to do is initial placement. This is nothing new. It will be placing the MDKs as they come into the data store cluster. But with the new version, with the vSphere 6.0, the placement also impacts, depends on the reservation settings of the VMDKs, as well as the overall reservations that are already consumed on the data store cluster. Okay. The second thing that storage DRS brings into the table is that placement was day 0, but these VMDKs will run, they will generate IOs, and then the IOs will not stay the same, they will change over time. If in fact the space consumed on a data store exceeds, or the IO becomes too heavy on that data store will overload it. In reaction to that condition, Storage DRS will look at and then move one or more of those VMDKs from that data store to other data stores in the cluster. And then everybody's happy. The third thing that Storage DRS does, it allows you to set some business rules. So you can say affinity rules between VMDKs. You can say VMDKs have to be the same on the same data store, or VMDKs have to be separate at all times. Once you set an affinity rule, the placement will respect that. And then in this case, we're talking about two VMDKs being kept together at all times. And when Storage DRS have to move that VMDK later on, that rule is still kept in place. Okay? The other property of Storage DRS is that it also supports a new primitive called maintenance mode. What you can do is that if you want to take a data store out of that cluster, you can put that into maintenance mode, in which time all the VMDKs will be evacuated from that data store to other data stores automatically. And the last but not least, if you add a new data store to the cluster, then Storage DRS will automatically recognize the performance and then of that data store as a resource, and then move some VMDKs so that the resources of the new capacity can be incorporated into the VM workload. Okay, so that was the really basics, and for those of you who are already using Storage DRS, that was nothing new and nothing exciting. So let's look at some of the interesting deployment scenarios that might arise with Storage DRS. So what I'm going to do is I'm going to go through first what happens with some of the advanced capabilities from the storage side. Then what happens with some of the replication capabilities of the vSphere. Okay, let's start with storage side. So thin provisioning, nothing new. So let's just start with a simple example. Let's just say I have a data store with 1 terabyte space. As you all know, you can create VMDKs in different formats. So the very simple one is you can have a thick VMDK. If it was 500 gigabyte, it will consume 500 gigabyte on that data store. You can also create thin VMDKs. In this case, let's just say we have a thin VMDK of 500 gigabyte configured size, but only 100 gigabyte is being used of that. So if you put that VMDK on that data store, well, no surprises, you only get 100 gigabytes used. Another one, same story. So let's just look at what happened here. Okay. We had a 1 terabyte data store. We added 3 VMDKs, and we are only using 700 gigabyte. But the total amount of VMDKs that I have provisioned on that data store is about 1.5 terabyte, which far exceeds the capacity of that data store. Okay. So how does Storage DRS sort of captures this? In the case of the Storage DRS, the capacity is captured as something called a space demand. What that means is that it's neither the used space nor the provisioned space. It's somewhere in between. In the case of the Storage DRS, there is a default configuration option, which will look at, for any thin VMDK, you look at the configured size but not used. And then you use 25% of that unused capacity as a space demand. So in the case of the Storage DRS, even though 700 gigabyte has been used on that data store, we look at as really 900 gigabyte being consumed. Okay? What this allows you to do is it allows you to fine-grain and fine-tune the actual space consumption on that data store. Okay? This was all and good, but you know what? Storage arrays do the same thing, don't they? In a modern array, you can have a storage array, and then you can have 3 data stores. Each, let's just say, for the sake of example, they have 4 terabyte capacity. As you put VMDKs on, those data store capacity will be sort of allocated. Underneath the covers, what the storage array will do is that there's a backing pool to cover all those data stores, just like we have done for VMDKs. And you don't have to allocate full 12 terabytes to capture that 3 data stores. What these arrays will do is that they will keep adding, the storage admins will keep adding the capacity to the backing pool as the data store gets filled up. So this is all on good. I haven't done anything. I described the same thing in the VMDK level. Now I describe the same thing on data store level. So which one should you use? So the answer is it really depends. Okay. If you use the storage DRS level at the VMDK level and use the storage DRS for controlling the overcommitment for space, what you have is a fine-grained control of how much space overcommitment on that data store. If you use the data store level, it's really not a problem. This is one of the common deployment scenarios. Storage DRS actually, in those cases, really understands the actual space consumption of that data store. So there's a protocol called VASA, and if the array is VASA capable, it will tell storage DRS how much of the backing store is actually being consumed. Okay? Depending on which version of VASA you're running, in the case of the version 1, there will be a signal coming to the storage DRS. As a result of that signal, storage DRS will stop using that data store if, in fact, the backing store capacity is running low. In the case of the version 2, storage DRS actually gets a bit more intelligent and will understand which 2 or 3 data stores are sharing the same backing pool, and then will make migration decisions appropriately to understanding. But just to drive home the actual lesson here, which is that, team provisioning is a really great thing. You can use either at the hypervisor level or the data store level. Both of them are fine. But the thing that you should be aware of that, use one of them. Don't use both, because then you might end up in a situation where you think you have overcommitted, let's just say 2x, but you might in fact be overcommitted by 5x. That would mean a lot of risk in terms of this capacity consumption. So team provisioning was one of the space saving features, but what about deduplication? The most modern arrays comes with a capability where they compress the space based on the content of the data that is stored on that data store. So for example, if you have 3 data stores on the left and they are deduped on the same data store, the actual space consumed on that data store will be much less than the total amount of data that has already been written on that data store. Okay? So, okay, this seems like a good thing. What is the problem? The problem is that if you look at the total space consumed on that data store, you have, you are actually storing much more than the capacity. Don't worry. So storage DRS actually understands this condition, and it doesn't affect in terms of its actual management of the data stores in the cluster. What happens in the new integration with the vSphere 6.0 is that if the data store is really VASA capable in the new version, storage DRS actually does manage in terms of how the backing space for that data pool is being consumed. Okay. The third thing, how about auto-tiering arrays? So we talked about performance, we talked about latency controls. There are advanced arrays that can actually do the latency controls at a much finer grain than storage DRS. Recall that when there is an I/O performance, the way storage DRS alleviates that I/O performance is it moves entire VMDKs from one data store to the another. But with an auto-tiered array, you don't have to actually move the entire VMDK. You could just move a couple of blocks within the VMDK underneath the covers, and then you get the same benefits as moving sort of like the entire VMDK, which is a great thing. So what happens with storage DRS? Okay. Now let's look at the basics again. No matter whether or not the data store is auto-tiered or not, what would happen is that there is you'll see on most arrays a curve like this. As I/O load increases, as I already mentioned, latency will go up. Okay. With an auto-tiered array, there's an additional bonus. What that means is that latency will go up, but then array will catch up later on. It will push the latency down without actually changing anything at the same load level, because it is able to look at the data store load and then optimize it based on the actual characteristics of the I/O workload. So in an auto-tiered array, suppose you use storage I/O control, and then let's say you set a threshold at a certain level. What storage I/O control does is, once that threshold is set, no matter what happens to the workload, your I/O latency will never exceed on that data store above that threshold. Okay? How about storage DRS? Storage DRS has an additional threshold too. What it will do is that it will just work with work with the array to further reduce the latency, even without going through it. So the problem is that when the storage DRS and storage IO control is doing the latency control and pushing down the latency down, they have to operate with the array such that they have to give the array the first shot at reducing the latency. Once that is done, and if the array cannot reduce latency beyond, at that point, then they can get into the picture and then, take some load of that data store. All right. So one thing that is coming up in the new release is that the configurations of storage DRS actually become much more fine-grained. So previously, you could only set, here's the data store cluster. You could just say automatic or manual, and that was it. Now, depending on the characteristics of the move, depending on the type of move, you can individually set the policy level, the automation level of the moves that the storage DRS makes. All right. So we talked about the array side of things. What happens in the storage deployments are a bit more complicated than your usual vanilla storage arrays. What happened to the replication? Okay. So let's start with the array-based replication. What that means is that, let's just say in this example, we've got a primary side on the left and a secondary side on the right. So what storage SRM does is that it replicates the data stores between those two sites. But as it might happen, the individual data store replication policies might be slightly different. Okay. Previously, to be able to use storage DRS on the primary side, you have to make sure that all of the replication policies of the data stores has to be exactly the same, then they have to be exactly the same consistency group and things like that. Okay. With the new version of storage DRS, those restrictions are going away in a way that now storage vSphere SRM will tell storage DRS what is the replication configuration between those two data stores. Okay? When those configurations are received by storage DRS, it will look at, okay, so can I make that move? If the move between those two data stores can be made without any loss of protection, without any impact on the replication policies, then storage DRS will do it. But if there is any possibility that there will be a configuration mismatch or there will be a slight loss of protection for an interim period for a short amount of time, storage DRS will not make that move automatically, but it will make a recommendation. And those recommendations will be tagged as, okay, well, Mr. Admin, here's a recommendation that you should be doing, but be aware that if you do it, there might be a slight loss of protection when the protection policy catches up on that data store. Okay. So this is by all means the only way you can do replication across two sites in vSphere environment. The other method of replication is vSphere replication, where replication happens not at the full data store level, but on individual VMDK level. So for example, you can say that the 4 VMs that are running on the left, only 2 of them are replicated on the secondary side. So what happens is that on the secondary side, the replica copies of those VMDKs on the primary side are stored by vSphere replication. And up until now, for the 6.0 release, storage DRS did not know those extra additional files that are stored on the secondary data stores. So if you happen to have the data stores on the secondary side as part of a storage cluster, the space balancing or the space consumption of those things were not ideally movable by storage DRS. In the next release, what is happening is that the vSphere replication has gained the capability to move the secondary copies of those VMDKs on the secondary side. Okay? So storage DRS is aware of that, and storage DRS integrates with the vSphere replication in a way that when the space is being consumed on those secondary side, it will give priority to move the secondary copies of those VMDKs because they are secondary copies, they are cheap to move, they don't have any production impact as far as the primary is concerned. Okay? So no matter which site, primary site or secondary site, now you can sort of like, deploy Storage DRS without any worry about what are the replication policies, whichever replication solution that you use. Okay. So before I conclude, I just want to remind you a couple of best practices that you should be aware of. For storage IO control, you already know that, like, when you are using storage IO control, make sure that all of the data stores that are used by storage IO control is used by vSphere alone. There is no mixing between the physical workloads and the virtual workloads for those data stores. Okay. For most of the configurations, I think you should just leave the storage IO control settings to default, which will be, it will look at the IO capacity and then will do the right things. But if you want to do, settings yourself, that's not a problem. And finally, if you keep the congestion threshold, if you happen to set the congestion threshold manually and then set it to low, there's an impact of that one. The latency will be low, that's for sure. But you may not be getting the full capacity of that data store in terms of throughput. Okay. For data store cluster, again, similar thing. You can put many variety of different data stores into the same cluster. But when you're putting multiple data stores in the cluster, make sure that they are roughly the same performance. Don't put like very varying characteristics in terms of performance or very varying data management characteristics between data stores. In terms of connectivity of those data stores to the individual hosts, so far as Storage DRS is concerned, partial connectivity is okay. We don't really care in terms of like, what's the connectivity of those data stores to individual hosts. It will be okay, but it will be awesome if all of the data stores are connected to all of the hosts. This is important because then Storage DRS has the full benefit of looking at the maximum freedom of control when it is fixing a problem or fixing a latency control in that environment. One last thing before I close is that, so previously we have I'm sure you start using the vSphere storage profiles. Up until now, we have supported single storage profile per data store cluster. With 6.0, that is changing, where you can have multiple profiles on that same data store. And whenever there is a recommendation that is coming from Storage DRS, it actually understands which profile that VMDK will consume and then react accordingly. Okay, with that, let's summarize. So hopefully, what I have conveyed to you is that there is a rich set of controls in the vSphere environment to be able to control in terms of how much a VM performance gets, and in terms of managing the overall storage consumption of the VMDKs on that data store. Okay? There are exciting features in play. There's IO reservations are out, and Storage DRS is better integration in terms of the storage features as well as the vSphere solutions in terms of replication. Many of these things are already in beta, so if you happen to use them, and if you have any feedback on these features, if you want them to be improved, let us know. So with that, I'm going to close and start taking some questions. So there are some microphones on either end of the room. So if you have a question, please bring one of those microphones. And also, don't forget to fill the survey for this talk.